Hello dear students of the University of Cologne. Among other things, this is the first experiment you will be doing here in our laboratory. Measurements on radiation protection. You will need various radiation sources. Uranium glass, beautiful uranyl nitrate crystals, an enclosed Americium source, metallic technetium, and a ruler and a measuring device. The first thing we will do is measure the dose rate. For all practical purposes, this is the parameter that tells us how dangerous the radiation emitted by a radioactive substance is for us. With the uranium glass, we measure approximately 0.25 microsieverts an hour. But sometimes only 0.2 microsieverts an hour. You can add a measurement value of 10 centimeters, but well, that's background. On contact, we measure 0.8 microsieverts an hour with the crystals. At a distance of 10 centimeters, we measure nothing. And with a plexiglass panel, still nothing. With the calibration source, we measure on contact approximately 8 microsieverts an hour. Since the counter tube is installed a little higher in the device and we can already measure somewhat high radiation values here, I put it on a pedestal. The measurement is 0.6 microsieverts an hour. Plexiglass shielding does not change much. At a distance of 1 meter, you only measure background. Now the technetium comes out. This is an open source, and technetium contamination is no joke, so you should avoid any contact with it. But even there, no dose rate is to be measured. That's interesting. We will deal with the blue barrel after all of our normal experiments. Now onto the activity measurement. To do this, we set the COMO to net counts and no longer measure with the Geiger-Miller tube built into the front, but with a scintillation counter built into the bottom. At a distance of 10 centimeters, we measure approximately 31 IPS, impulses per second, or CPS, counts per second for the English people. If we place a plexiglass panel in front of it, we suddenly no longer measure anything. That's interesting. With the uranyl nitrate, we measure approximately 350 CPS at a distance of 10 centimeters. With a plexiglass panel in front, we are measuring nothing. Seems like it's the same type of radiation. At a distance of 10 centimeters, the calibration source has a significantly higher count rate of approximately 1300 CPS, which, interestingly enough, is halved by plexiglass. Yes, honestly, I believe I should have left it on the pedestal in this case. But with a small lead castle, you can shield the radiation completely. With technetium, we are in completely different orders of magnitude. 13,000 CPS on contact. Sometimes it's completely overloaded, and then you put a plexiglass in front of it, and at a distance of 10 centimeters, we're measuring absolutely nothing. And now onto the big boy, the blue barrel. The blue barrel is our treasure trove for all kinds of uranium and thorium containing waste minerals. The problem with this is that it's big. It releases large amounts of the radioactive gas radon when it's opened, and it's just bulky. That's why most people in our lab are reluctant to do anything with it, but it's perfect for today's experiment. Once opened for the video, you can see that some things have definitely been laboriously classified, but some are just collections of loose minerals that have not been classified. So on contact we measure approximately 5000 CPS, and this then decreases with increasing distance, until we now measure approximately 750 CPS at 60 centimeters. The dose rate from the barrel is 80 microsieverts an hour at this distance, and at 10 times the distance, it has been divided by 1/8. And now onto the sponsored part of this video. We will measure the whole thing with the Radiacode 103. The Radiacode is a fairly fast scintillation counter, whereas we just measured with a Geiger-Miller tube and a scintillation crystal, depending on what we are trying to measure. This time the unit is not IPS, impulses per second, but it's CPS, which is simply just the English translation, counts per second. Since the detector is not installed with offset, I was able to measure a 0 centimeter distance and see very nicely how the count rate measure decreases until we still have increased values at 3 meters distance. In our laboratory, 6 to 10 CPS is normal for the Radiacode. If we now measure a dose rate when coming back, we notice that we will start at 0.7 microsieverts at 2 meters, and then it continues to rise. What a surprise! In this case, I actually wanted to show that we can still measure it quite well at a distance of 2 meters, and this is not a negligible amount of uranium. If you wanted to do environmental measurements, you should take measurements at least every 4 meters, otherwise you could simply overlook our blue barrel with a few kilograms of uranium in the worst case. Just to throw that into the room in case you are looking at some side surveys the next time made from other people. When you get close to the barrel, you can see fluctuations of 120 microsieverts an hour because the blue barrel is not homogeneously filled with radiation sources. But just to give you and our students an impression. So what are the findings that you should draw from this experiment? The measurement of the dose rate was actually more to show that very few things in our laboratory can emit a lot of radiation when handled correctly. In terms of radiation protection, the blue barrel is the most questionable thing to show in the video. Of course, we have way more active things than the blue barrel, but this is the first day for our students in the lab. The activity measurement, together with types of shielding, is now a decisive factor in giving us information about the type of radiation. Let's start with uranium glass and uranyl nitrate. If you look at the chart of nuclide, you can see from the yellow color that uranium-238 is primarily an alpha emitter. But the alpha radiation is not the one that we measure, as this is shielded by either the glass itself or the plastic packaging. But what did we measure? Betas. But where do these come from? It is chemically purified uranium. The uranium decays into thorium-234, and this almost immediately decays into protactinium-234M. And this then decays into uranium-234. And that's the end of the line, as this does not radiate much further due to its long half-life. This means that between uranium and uranium there are two beta emitters in the decay chain, and especially the radiation of the protactinium-234M is quite high in energy so that we can measure it. Gammas are not emitted by any of them, and we are just going to ignore the X-ray fluorescence for now, because we will learn about that later in the practical course. That's why we don't measure anything through plexiglass, because beta radiation is shielded by it. So in conclusion, chemically purified uranium, for all practical purposes, is a pure alpha and beta emitter, and it also does not emanate radon gas. In the case of Americium-241, we can see from this tile that it is an alpha emitter. But again, it's wrapped in plastic, so we don't measure alpha radiation. The radiation also seems to get through plexiglass, which means it's unlikely to be beta radiation. Accordingly, it can only be gamma radiation, and that is shielded by lead. In contrast to uranium-238, Americium-241 has significant gamma lines. In the case of technetium, we can read from the color of the tile in the chart of nuclides that this is a beta-minus emitter. And with the plexiglass, we can then confirm, for all practical purposes, this to be a pure beta-minus emitter, without any gamma radiation. The blue barrel contains untreated natural uranium, with the complete decay series. This is an everything emitter, but only the gamma radiation can get through the wall of the vessel. This is quite a big emitter, and mathematically speaking, at very short distances you wouldn't be able to see a drop in radiation exposure, but only within the few first centimeters. In the extreme case, with a very big blue barrel, you wouldn't be able to reduce your radiation exposure just by stepping back. And now on to my professor's favorite question at the end of the day. Which of these radiation sources would you most likely eat if you had to, assuming that you want to minimize your radiation exposure? I'll just leave the question to be answered in the comments down below. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!